Welcome everyone to Practical Lecture 3.1. We have our second part of building scalable machine learning pipelines with Apache Spark in our Practical Lecture 3.1. As Practical Lecture in the course, we really do much more demos. We go to real software, real cloud vendors, demonstrate something. Of course, it's clear we're not paid by them, so it's basically sort of a demo to really show real cloud vendors out there that is actually are used in industry and in commercial setups on a daily basis. At the same time, we also want to transfer some knowledge about machine learning, which is an extremely rising theme, as many of you have noticed. So in part 1, we clarified already some, let's say, foundational machine learning building blocks. Something about a target function that we will never know, but something like this that we don't know has created this data, right? It could be whatever. It is something which we will never know. Hence, it needs to be still something to discuss later, maybe also with a probabilistic assumption, but we come to that later. We have this target function and we know it generated data, but data is something we can look at. And we did in the first part. And exactly this is what machine learning is all about. So it's learning from data, if you want. And that's true for deep learning as well. However, one key message to take away, I hope, in this part and also in the next part is really thinking about that machine learning is not yet another algorithm you throw at data and you are done. And that's why we had also at the beginning of part 1, and we will continue in part 2, the CRISP-DM model. It captures nicely the idea that machine learning is a process. It is about algorithms. It is also about learning algorithms that basically over iterations converge, not converge, etc. But the essence is you cannot just throw data at machine learning. It will not work. You have to work on the data. You have to inspect the data. You have to prepare the data. You have to identify features, do feature engineering. So instead of repeating myself maybe too much, it's important to understand really that machine learning is a process of working with data. It's not just one function you call and say, fit, done. So and this, I think, is nicely captured by this CRISP-DM diagram and also by, hopefully, the foundational blocks that I'm basically presenting you throughout this lecture. I'm presenting this since, I think, now 10 years at least, and got very good feedback that people know a little bit what, all the different elements are, what we don't know, what we know, what is the computation intensive stuff, what is the storage intensive stuff, and so on. Now, thinking about going one step more that we had in the first part, we want to know start of learning. We did inspect the data a little bit. We understand the Chicago food inspection example, which is sort of a HD Insight example. But we clearly saw the idea of saying there's a pass and fail assumption. So in a way, a binary classification problem. If you have 50 classes maybe you want to do, then maybe logistic regression would be not for you. You would go to SVMs, or more notably these days to artificial neural networks, deep learning networks we're going to use basically often basically in research academics and also in many commercial settings today. And in fact, will be also part of lecture 6 and lecture 7 for you. So we will make the move at some point in time, but as I promised you, let's start simple. And linear learning models are linear in weights. That's why I always say linear learning models. You have to think about this. It's an important factor. It's a linear learning model because we learn this here. We also had the idea of this hypothesis set, and students over years now always ask what exactly is that, right? And we will come to this also throughout the course. And of course, in machine learning seminars, I go much more into it, but you can think about it that you have a freedom to choose. Like H1 might be linear classification. H2 might be linear regression model. H3 might be logistic regression, but also the different H's can stand for different parameters. And you will see logistic regression learns certain weights in this learning model. We call that also coefficients sometimes. So basically what goes with all the inputs, right? And as I said, it's summed up linearly using weights here. And these are sort of the coefficients we identify, we learn. And output should be then something like pass or fail in our example. So hence we put it to this interesting logistic function that you see, takes the dot product, which is nothing else than you see here, summed up linearly using weights. For mathematical convenience, you have the W, basically transpose X or the dot product. It's basically equivalent in mathematics. And by steering these different weights, as you have seen throughout the beginning of the course, we have different H's. So whenever basically this weights change, you have also different hypotheses. Hence, this hypothesis set is huge. You would say, in a way, given all the parameters, given all the weights to learn, it's sort of infinite. So it's not only captures the essence of saying, I pick SVM, I pick a decision tree, I pick a random forest, I pick a neural network of sort, I pick a logistic regression model, but it also depends of how, in the end, basically this hypothesis then will be trained on the different coefficients and basically the different parameters you will be basically using to steer the different learning models. Do you use a 20 hidden neural network, which would be questionable, or you use a transformer model, or you use a neural network with 2 hidden layers? So all of these hyperparameters, which we also will look in lectures 11 then, right? When we think about later data mining, and then later on in the lecture, there will be a lecture on hyperparameter optimization itself. These topics will be becoming more and more obvious to you. So, however, here for the course today, and also for the practical example, we stay with logistic regression. Very nice, simple material, nice fit function, logistic function, and so on. And I think we understand now that we want to understand, the model that really gives us, the result of the Chicago food idea of all these different complaints, whatever, and give me out, would it fail or pass? And this is something what we want to look at now. So hence I switch again to the practicals. So let's see where we are. And again, it's hopping around between the practicals here, but you will understand that mostly I already have put everything in the slides you have basically also here in the active live demo. In the end, it's also nice to see that you have queuing here, right? So it's actually happening and waking and waiting for doing something, which then is something I also want to show what you can do when you do your assignments and so on. Sometimes it pays off to do, kernel ready, you see, reconnected or so. If you sometimes not use it, what I would not recommend, do the assignment in one go. You can always do something called kernel restart and clear output, right? So by doing so, everything we've done before is done, is gone. But that doesn't matter in a way, because the environment is still there for you. The HG Insight cluster is ready to get your commands. So we're starting in the yarn and so on. And then we'll go back and we'll, continue with this. So this can happen when you do the assignment. And also because the assignment is very costly, you will notice when I put it in at the description, how you can access a resource group, we have some certain intervals and some certain time, because if I would now let the Spark running, you can imagine $4 or €4 actually per hour, 24/7 for you for a month, that is quite some money. Hence, this one particular part of the assignment is loaded and will give you some certain windows where you basically can work on it. And this is negotiable. You can, contact my assistant and we will talk about it. If you want to work on this assignment for, let's say, this particular day, you get rescheduled and we open it up again. But more on this is on the add tool, and I will basically also come to this and in the, let's say, third course hours. You see, we repeat here many things. This was all was documented. So let's go a little bit also to the slides. While this is all running up again, because we're waiting a bit, and then it could be that, it's idle, waits, and takes a long time to re-go, we want to understand if it's really, a binary classification problem. So if you think about what our initial data analysis was saying, that sounded like this, pass and fail. But if you inspect the data, and that is an important part of it in machine learning, you have to go again and to look at this. So here are some results, which are our labels, right? Results is a label of the analysis of this food inspection. And you see there's fail, business. Actually, we could not even find it. It's a bit funny, but US is large and Chicago is large. So PAAS without conditions or with conditions, there are different classes really, and one is even out of business. So hence, we can see this is not a binary classification problem. But in a way, our goal is still to do it as a binary classification problem, right? In a way, we want to say, will it pass or fail? Everything else, if they can't find the business, or if they are already out of business, I don't care that much either, right? Let's say you have a restaurant, you have lots of complaints on Twitter about your restaurant, and you want to know, okay, well, is that something where I will pass or fail? If I throw it into machine learning, does it give me a prediction if it will do? Hence, you see here that sometimes we can also think about this a bit more and see, can we not turn this 5-class problem that we have now in essentially binary classification? And this means we can maybe summarize some of these classes a little bit more and see how many cases are there really on these different elements. Hence, we will come back a little bit here. I just will do this here. Then we have our inspections. That's what we did already in the part 1. And the data frame. We look a little bit into this. Of course, if you have questions about several different parts, I encourage you also to use the add tool. Maybe also more students will see, and I do my best to answer these questions. Here again, you see basically nicely for fail pass. So it was suggesting a binary problem. But if you look in all the data more intensively, and this is what distinct is showing here, right? Distinct shows how is it different from others. It shows you quickly, oh, the results that we pick here with the data frame, select just this row. Going through all the data, and you see suddenly Spark is doing some movements of having already 4 running jobs, because it has to go through all data. Here we just picked the top 5, very simple job. But here we have to go through all data to understand what is a distinct. So what is there some value that was never happening before? And that's where we came across the 5 classes and say, well, it's actually not just fail and pass, it's actually 5. So hence we have to do something. We have to work on thinking about, and this is also documented in the slides, of course, how we now do maybe with accounts and thinking about, can we not summarize a couple of things or even deem some of them as not really important for us? And here it's where SQL comes in. Right, you see a little bit how that works when we think about the results here that we have now established as a table, really. And by doing so, we can go and analyze this, and we want to basically have just the count. You see this as a select statement. It's SQL query. The query language itself gives you a count option to understand now how many are there really in all these different classes that we just have found out today. So we see many of them fail, and many of them, even much more, double of them pass. So in one respect, we hope that the majority of restaurants, of course, should pass, because otherwise Chicago would have a problem, right? So, I mean, if the most will fail, then that would be not good. Of course, pass with conditions, in a way, you would say they still pass, right? And the restaurant owner would be probably very inclined or very happy to fulfill these conditions to keep his restaurant open. So hence, you can even say this 8,400 samples, as we call it, right? Samples, all these different data items. How many of them are there? We can summarize them and say, well, it's like 9.5, 9,500 that pass. In contrast to 3,000 that fail, roughly. So, and this gives you already an order of magnitude. It gives you an understanding. Maybe we want to summarize these 2 classes. And it seems like this business not located, out of business are anyway corner cases, right? That this is like 206. I mean, business not located is really funny, I think, as well. But in Chicago, you never know. So hence, we have an understanding of thinking a little bit about maybe data visualization gives us more. And that's what also is often done. If you remember, in this CRISP-DM model, data understanding is often very much also supported by data visualization techniques. I just want to give you the insights how it is in real projects. When you work with industry, your boss can come in and what happened, for instance, in competence center is academic, but doesn't matter. It's the same in industry. I want infographics. This is a new term here, mostly for statistics on a very condensed area, and I'm sure you have seen some of them, right? You see that here is an example of infographics, or this one, very abstract, of course, but the idea is to show very much statistic on a very little space in a very graphical visualization manner. Hence, not only anymore this funny pie charts that you had maybe in the past, you would integrate this directly with other, graphics you would have, with other statistics you have, in a very, let's say, condensed manner. This is sort of the way how, in the moment, many of these companies and also academics work in terms of reviews, in terms of getting money from superior, let's say, lord and masters of your company or shareholders that want to know statistics. Are we on track? What's happening with customers? What is sort of things? In our example, we stick a little bit here with our infographic in terms of the simple pie chart, still nice, where we see a little bit what is, of course, was also already, if you remember, in the table here, we sort of expect the same pie chart of saying, well, actually, luckily, many will pass, right? So there are many things that would be maybe true positive, or say, well, yeah, we predict they will pass, and hopefully we will also later on say, well, that will be also someone that is passing, given all of the majority of data. But there are some of them that fail, 1/4 of it, and then we have this out of business things and so on, which are almost negligible. Still, the pass with conditions is something what we can maybe incorporate in, make it even more bigger footprint that the majority will pass. It gives you an important understanding, but also for us, it's now meaning we have to, let's say, prepare for machine learning the data better. Hence, the labels that are giving now fail, pass, pass with condition, and blah, 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 etc. We have to refine as a little bit as you see it here as a 10,000 feet perspective, right? We say now one class is 0 and fail. That's pretty obvious in the data. But there's another class that says pass with conditions and pass that could be summarized together. And you see a little bit how that works now when we come back to our assignment element here. There's basically now the idea of combining that together and have this as labeled data directly, put into practice, so to speak, to basically see there's a label to it that will be basically then giving you the idea of the summarized element. You return 0, 0. If it's fail, for instance, here's a label, right? 0, 0. So that is a failed data set part. So one sample I pick from the take one. You'll see all the complaints here. That is a normal data. So hence we have, different types of violations here, etc., etc. But for us, it's in the moment not the case. For us, it was much more the label of saying if it's pass with conditions or pass, then no matter what, we just see it as 1. Then we say basically, everybody who's failing is getting a 0, like this one. And then there are these sort of things, if you remember, which are not both out of business and not locatable. Then we turn -1. This is sort of an artificial label that we use to filter it out, right? You see labeled data frame, select all the labels, blah, blah, blah. And then, we do this where labels is bigger than 0. In other words, we filter with this -1, this out of business out and not locatable. Because in the end, this will not give us a guided supervised input, right? It has nothing to tell us if it will pass or fail. It's just, in one respect, we would call it noise, right? It's noise for us in machine learning because we cannot really learn from it. Of course, it's still data to keep. It might be, you never know what future classification schemes will come about with some insights, but here in the given problem at hand, it will be not adding too much insight. And in a way, this is all documented on the slides. Apparently, of course, if I have a practical lecture, I cannot go one by one exactly what is on the slides, but you will see what I discussed here now is basically bringing the stuff together, having the labels, and now we want to think about that classification algorithms exists. Just a short connection back to our, conceptual lecture 3. We have learned there are many different algorithms in the machine learning library, and we will also in later parts of the course look, for instance, at recommender engines. But for this classification, there are different algorithms existing, and logistic regression is quite of a nice, simple algorithm that captures the essence of machine learning for this simple problems, especially for binary classification problems. Hence, that's how we come now to the implementation to it, right? So, and this is now a next step in a way. It is, again, the difference now that we have thought about logistic regression as a hypothesis set, could work. But for us in parallel computing and in distributed computing, cloud computing, etc., we need to have an implementation of this. So where it's existing. So as I told you earlier, if you do scikit-learn or something like this, a serial implementation, and use this with 1 petabyte of data, you will quickly fail. It's not parallelizable. It's not scalable. It works for small data sets, no question. And maybe it works even better for this, because then you don't have the overhead of creating a cluster. You don't need to scale, but you sort of limit it to the memory at hand, right? And this is, of course, something where then Spark really points for big data, hence a cloud computing and big data course name. But I think that's more or less getting obvious to you now. I see the questions and all the breaks where we discuss, and I think the majority of you now captures this, that of course you would use Spark only in a way if you really swim in data, right? If you have, let's say, a couple of bytes and you want to basically have a text file and have this similar situation with pass and fail, maybe also food inspections somewhere, there's no point of maybe necessarily going to Spark. Hence now we pick the hypothesis set part out and say we take the hypothesis of logistic regression. But this means also, in terms of picking this hypothesis, you have to agree on a regularization parameter. Regularization is helping to basically generalize better in machine learning. It's a topic which requires usually like 2 or 3 university lectures, so I can't go into much details. I refer you to a machine learning course, but in generally that's an important thing combined with validation to combat overfitting and the different traps in machine learning that a proper machine learning course needs to teach. And there are other, let's say, hyperparameters in one respect, how many iterations you want to do to learn from this data. This could be also make a big difference, especially if you have large quantities of data and so on. So hence we do the connection between the implementation and the hypothesis set, where we picked one hypothesis, right, making it h of x, where we put the logistic function now, making it logistic regression. But this is just a model, and we learned it needs to be an algorithm, right? So logistic regression, and formalize this here a little bit and putting now the pipelines into perspective. But let's stay here. Logistic regression is what we know. So it is iteratively solving this optimization problem. We have lots of, W's we want to adjust. And by doing so, we will always have our guiding why, that, we can check and are we on the right track, or we do have to change and update the weight, vectors in a way. So in other words, we set the coefficients of the logistic regression more accurately over time with iteratively going through it. So here's where the learning takes place. That's what you learned already before. Has something to do with an optimization algorithm, SGD. Today, people use ADAM and other optimizers. So this is a big field in itself. But to come back to the idea of now what we think about pipelining, let's go a bit back to the practicals here. Now we have this labeled data, and we do this interesting step like a tokenizer. So we use all the violations, and we have this basically as a token in terms of words, and do a sort of hashing idea of it to make a sort of very condensed feature vector. So I would encourage you also to read up on this particular function, right, where you have this and would say, this is something, of course, where we have now a condensed representation of many of these violations, where you essentially go. And you notice I maybe waited again too long with this. So as I said, you have to basically go consecutively through it from the top. So we can again maybe say rather clear output to not wait too long and go from the top again. It's not a big problem here. We have still some time at hand. So you see connected, trusted, kernel ready. This message is here on the top. And we'll, recreate our runtime. This is a bit inconvenient in a way, but also, of course, people would usually not teach alongside the way, but rather use that Jupyter notebook. And also when you do your assignment, you will notice I said you should put in the cell the idea of the text, where you say you comment on it, what is happening in the cell with your own words, right? Hence don't bother, maybe don't even go to something else, another text, you know, or whatever. You can do this. I'm not having a strong opinion on this, but maybe the simplest is just you work with this kind of Jupyter notebook, as many people do. You will see also sometimes tutorials are already completely on it. So not sure why there's now an error. We have to see, there's something not really working right now. Let's say we basically maybe better say close and halt here. It says also no kernel. That's also an indicator of there's something wrong. Could happen sometime, especially if you wait. Here's something with autosave failed. Who knows what exactly the cloud here and there is doing? Could happen with these. So we go back to this particular Jupyter notebook site and we'll see, you know, the cluster seems to be still running, and refresh a little bit. Okay. Whoop. So let's see if we not just, you know, start again from here, start the Jupyter notebook environment. And this is, of course, because all of it is remote and it has certain timeouts of browsers at certain timeouts in different elements. Something like this could happen often in this cloud services, right? So don't keep the tab open necessarily. Firstly, because it can mean also lots of costs. And secondly, it might be also a bigger problem of, you know, doing this. So let's do here clear output and start new. So connecting to kernel, and it seems to be all right. Kernel ready. That is our sign of really trying it again. And it looks good. We're starting Spark application this time. So let's see how it works. And then we will do maybe continue a bit more on the script and, you know, try to do then the description later on with the slides. Just while we are here, think about now that the pipeline idea is now to think about the bigger picture, right? That means you have the data coming in, and you want to, you know, have this kind of words that are very difficult for mathematical convenience. So you're hashing them into a very nice feature vector, feature vector that we basically give to logistic regression to learn in terms of mathematics, steer the coefficients. In other words, you have the raw text, then you have some words here, you're hashing them, creating them a very condensed feature vector with lots of high information value. And what's coming out by iteratively learning and boil down the error with all the different updates of the weights, you have a logistic regression model in the pipeline at the end. That's a training process. Hence, there's something what we want to do basically and show you now. We have now a Spark session back. And let's go a little bit here quicker through. So this is done. We'll do an inspection again. There's some repetition here, but it's, I think, also good to understand that it's all remote. So it could happen from time to time that you have to reconnect, that you have to restart the cluster, and so on. And it's not necessarily that the HD Insight fails, it's just more the connection to it and some timeouts, which are actually there also partly for security reasons, but also partly for you know, keeping the consistency, what you see in the Jupyter notebook, and the results that you see here with the jobs and everything. So it's in a way something where usually people would, of course, work with the Jupyter notebook and not go back and forth to slides a lot. We have been here basically counting the results and just repeating what we already have discussed essentially before. And that's a good example of having now several jobs, right? Because we have to go through all the data, not pick the top 5 or so. Then we come here with the idea of understanding, well, many of these will be probably lead to a PAAS, but we have to do a classifier that is actually doing something, and we want to merge the different classes, things we discussed before. Then we take the labeled data again and understand now we have all these violations, this clear text. And this brings us back to the slide that we just had. These violations are lots of words, and maybe they're negative words, a lot of them, that give us an indicator, or positive words, that in the end gives us then the indicators as features, will it pass or fail? Hence, it makes sense to look at the words, but mathematically can maybe have a sort of hashing function for all of these words and have a more condensed representation of it, a mathematical value if you want. Then you see also here in this command, which is now loaded, we have a pipeline we create with all the stages. We have the tokenizer crushing the data right into words. Then we have this hashing function creating this interesting feature vector that we're going to use. And the pipeline really says then, okay, we have to have the logistic regression model with 10 iterations and this regularization parameter. And every time I say fit in a way, then you can imagine now the resources are really running. The transformation of data will also already take some time. Now the fitting the data will also take some time. So this is where the machine learning now is activated, doing essentially the optimization steps. Hence you see lots of jobs created. But the beauty is that after that, we would have a model, right? In other words, when you come quickly to the slide, not to have the environment shut off again, we have this logistic regression model created. We cut it the raw text into words, create the feature vectors, and from this, through iterative learning, we basically created the logistic regression model, and this in a distributed and scalable fashion, right? If I now have petabytes of data, this will take very, very long with 16 cores. Hence, of course, then you maybe want to increase the worker nodes. Hence, this is the idea of the scalability inside. Now, when you coming back basically to this, we have now a model. This is fitted. So in other words, we have the coefficients for the logistic regression model and so on, and it's regularized very nicely. So it should generalize to unseen data. And that is what's coming here in the next idea, test data. As I showed you before, in the one diagram, I said, well, we have the training set, we cut that, we use that for basically training now. Now we have another data set. You see that with food inspection 2, separated values, so that we basically use now the test set we throw away in the corner. Now we have our model fitted, but instead of just using it with a model, you can imagine we have the same trouble of the data still in pass and fail, pass with conditions. I don't find the business. So in a way, you have to transform the data the same way we did for training. But now we want to test. We don't want to fit the model, it's already fitted, but we want to check, we want to evaluate with a test set if the model is really good, right? And that is something now where you need something we call unseen data, something which was not in the training data. You would use a test set for it, and it should go through the same transformations of data we have done before. Hence the pipelining idea now, and you see this a little bit with the predictions here, right, that we do now on the test set. We use a model and transform it the same way with this kind of test data frame, which is a test set, which then already has done transformations and so on. We here just pick those, of course, with conditions pass or fail, and then it will go through the same transformations, making a feature vector, etc., crunching the words, and then having a template, a temporary table called predictions that we can later on use. Hence, this is existing. We have a couple of things here, the features, the raw prediction, the probability, and then the concrete prediction. Again, the probability is important. Remember the squash function, this kind of, having everything between 0 and 1. It will be rarely just 0 or 1. It will be mostly some comma values 0, 0, 0, 0, 1, or, like 0.9999. Rarely we would have 1 or 0. So there's a probability towards these classes. So let's look at these predictions, right? So just take one to get an indication how that could look like. And this is something where you see a little bit here on the end, probability density vector is here, where you can see the prediction would be most likely 0, right? So it's class 0, and this is an important part. to say, okay, this particular one has now essentially got a kind of direct prediction basically of probably failing, which was our 0 class, for instance. And of course, this is all modeling. You can do it the other way around. You can say, well, 1 was basically the one I meant for this, but you see a little bit then that you have to transform the data differently. Briefly, now thinking about the process which we had, you remember we had done this pipeline. It's often used in really commercial environments, this pipelining approach. Then you have a logistic regression model. But now we actually changed the view. We did the math, it was trained, it was fitted. That's something we already have discussed in one of the earlier lectures. So using optimization techniques, updating the weight vector again and again and again and again iteratively, always based on the label that can of course sum them up linearly using weight and then compare with the Y class that we have, and then in the other one now understand, okay, it's actually still wrongly classified and so on. So we update the weight vector, and over 10 iterations, we hope we basically have done something which is much better, right, than the initial idea of using these data maybe with a model, or we don't have really a model, we just analyze it with some weight vector that needs to be trained. So in other words, we now switching to this idea of after modeling it with a pipeline, and we have seen that was quite computational free, we sort of can formalize this a little bit and putting it in our diagram. We have now a learning algorithm, and we out of the hypothesis set, which we said is logistic regression, right? So we pick one G with specific iterations with a specific regularization parameter. That was one thing. But we put it through a learning algorithm to arrive hopefully at something which approximates F well. And if you know, F was responsible for creating the training examples. In other words, we would have something created which gives us basically simple labels, very similar labels that the training examples have. But remember, we're doing this now also for the basically test set. And we did the similar thing with a linear example in the perceptron model, right? There was a perceptron model with the flowers and the perceptron learning algorithm. Now we have logistic regression model with basically this stochastic gradient descent and inherently this optimization, doing the weight updates over time, and then coming to some coefficients of the logistic regression model that hopefully approximates F well. This target function we never know, but we will probably have something like this that the training examples will be most equally be classified. Hence, we put that in our learning diagram, in our practical machine learning overview, how that all fits together, what we need, what not. But there's more, right? And this is just an example. Now, of course, again, we had this idea in the beginning of the lecture of having now, the concrete weights. And if you do the exercise, you will see if the weights are there, like our coefficients now in the logistic regression model, when you put the data in many cases, it will be actually like the label. But maybe not in all the cases, right? Hence, machine learning problems are never really 100%. We also understood that there should be a certain error measure, right? So this is something we also don't really have yet in the diagram. So the logistic regression model was one thing, SGD was one thing, but we always have to have the loss function to really understand how far are we from the weights we learned. This is new every iteration, but we have also the guiding label Y. Right? And by putting this in the logistic loss that you have here, the logistic loss function, you will understand, okay, the error measure we use to knock down the error, right? To perform further iterations of the stochastic gradient after each of the iteration, and then also give us sort of the accuracy. Hence, we give something into this error measure, and this can be something you steer. You can have different error measures depending on severity and so on. Basically that you have to pick and also have basically you have to know and put it into the machine learning algorithms as a sort of informant to guide the learning really, right? Otherwise, if you don't have an error measure, you can know that from exams, from test exams, from practices. If there's no error measure, then how you improve? There's no yardstick, right? You want to improve across something. Gives me also the opportunity to say that machine learning, we don't really use a target function here. We have rather target distribution. Think about Netflix. You look the same movie, right? Lord of the Rings maybe 20 years ago or 10 years ago, and you look at now from the graphics, and you would give a different label. You like it not so much anymore, or you basically like it not so good as you liked it before. So machine learning has different ideas of having the same X in, but different Ys, which is not the function. If you remember, that is a function plus noise, something we have to learn, making it a bit from, different from statistics about, function approximation. Now, looking at this, we have done it now with a test set. I was alluding to this. We have seen results were failing here. And then, of course, it gives us also to a prediction of 0. We said this is a class for fail. In a way, a true negative in this sense, right? So failing. In other words, also, or basically at another illustration, really, we're reusing the logistic regression model here. As you see, we don't train anything anymore. But we use the same pipeline that we had before, but we don't need this training step because we're in the testing phase. It's already fitted the model. It has the coefficients. The whole model is just usable for inference, for predictions, and that's what we do. Hence, we have not this fit, and it's also not so computationally expensive anymore, right? So in many cases, often you would say machine learning training is expensive in clouds, in deep learning particularly, but if you want to use big, data then and do inference on a trained model, that is rather cheap. Now, to do model evaluation, which is one of the last parts really, and the idea of now thinking, do we do a better model maybe? Is logistic regression not capturing it? Do we get more performance maybe with another hypothesis? We can have out of our hypothesis set an SVM. We just don't use logistic regression. Support vector machines can do binary classification, and they do this particularly well. So maybe we pick then the next time another hypothesis set, but I need to understand a measure again, right? And this is something what you see here. And there are lots of different model evaluations. I was alluding to several of them also in lecture 2, if you remember, with F-score and whatever, precision, recall, etc. Or you do the kind of idea that is here today, and that you also look and should look in your assignments a little bit more to understand it really. It's sort of intuitive, but can be also a bit misleading because they're interesting words that seem to contradict each other. You see the true positive, false positive, true negative, and false negative here, which is sort of a confusion matrix if you want. I also documented this a bit here and would also go now basically back here before we lose the idea of the Jupyter notebook again. It seems we really again have the queuing. So I use my chance of here doing the kernel again and clear our input. That's a bit sad, but I think we're still sort of in time of doing it once more. And it's a bit also annoying part maybe in the clouds and, doing this, where you several times lose this context, but also in a way you should not do it like I do it always, explain something too long on slides or work too much on slides. You should work with the Jupyter notebook when you basically have activated it. So let's go once more through that. And then I think we are done. We're nearly basically also at the end of the lecture. It's just that the evaluation is something you should look into your assignment. And of course, this is a bit loaded. We have to explain it a bit with a couple of lines and so on. So while this is starting, again, I go quickly here through the slides. It documents everything. So we actually pick now and combine from the predictions that our model were doing and say to the original results and combine again fail and 0, for instance, here. And we can do this, of course, to collect this true positive that is here shown basically as a confusion matrix. So we have some actual values, of course, that we have in the data set, right? If you remember, that makes it supervised. So we know basically, will it be passing or failing? But we also have the prediction of our classifier that we can now put against these values. Hence, you have sort of 4 different options that can come out that are called this different way. And when you put it out here, you see a little bit, I printed that out and hard-coded the different ones here to get an understanding of this, that still, false negatives, failing, there will be many people passing still because, basically they are false negative. And then the true positive will be the ones that, probably, okay, based on all what we learned and so on, and the violations we found, it's a true positive, they most likely fail. So there's a sort of probability again, where we're not absolutely sure. right? So that's also important. Machine learning, as I said, it's mostly not really always 100%, it's a certain probability, and it gives you then also other possibilities here. So I finalized this basically practical lecture in one respect, really, by moving now just in the Jupyter Notebook. Again, what I do here in the Jupyter Notebook should be documented in Practical Lecture 3.1, which you then should use alongside really your assignment one. Hence, I give you the Jupyter Notebook already. It's uploaded. You basically have to do just a walkthrough, but it would be nice if you see a little bit of text, right, according to each of the different cells that I execute here in your own words. So please don't use my yellow blocks, copy paste it there. This would be meaning less points. What I want to hear is that in your own kind of understanding, and this needs to be not big poetry. So just keep it straight, a couple of lines, one line, whatever, what happens in the cell. So, you know, some cells are more elaborate, some are less elaborate. This would be good to do for the assignment. You load up the Jupyter Notebook. Then once you download it, so you can here say File, Download As, Jupyter Notebook. And when you do this, it will also have your execution inside, right? That's how I know that you really did it. And, you know, combined with the text that you can write in the cells, right? It's basically something you can edit. I basically have then your assignment, but of course, assignment one is more broader. We will talk about this in a minute when we come to the third course hours today. And then we basically can discuss how you upload it. I would also say you need a PDF maybe for doing the other parts of the assignment. And you have the other Jupyter Notebook that is actually mimics the idea what we had in the Google Colab. Because now you realize that the working in the cloud has much more to offer here. You have different jobs in parallel, while you see executing, you know, the bank example, for instance, in Google Colab will show you nothing of this. There are no jobs because essentially Spark is running in a local environment, not really like here you see a distributed environment with jobs and so on. And this is an important takeaway message. That the Google Colab is very good if you have a certain number of data sets, if you need computing at some certain level, but it will be never so scalable like in the cloud. However, of course, for cost perspectives, it might be a true and a very good alternative to do so, right? You maybe don't need a kind of Apache Spark cluster, which is so powerful, because, as I said also earlier, think about all the algorithms you have in Apache Spark, the recommender engine. So even if you don't swim in data and maybe Google Colab will be good enough, with a PySpark, you can nicely still operate in this environment, although it's not big data maybe, and can actually make effective use of the algorithms that you have. But yeah, we reached the end of the course also, I think, in this particular lecture, and I don't want to take it too long. You see here now the ideas of the different true positive, false positives, and so on that we queried here with SQL as counts from the predictions, also where, of course, the result will fail and or not fail, the PAAS, so how you generate then the true positives from the false positives. And to describe this a little bit, and perhaps also as I finished now here with the demonstration, I think, and put that in the perspective of this particular confusion matrix, to understand this a bit better would be also a good idea to describe. Finally, just a pointer, in lecture 11, I will be talking much more about recommender engines, also in basically Apache Spark again, and what's the benefit there. Yeah, I think many of you will know what recommendation engines are. It's basically you have customers or movies, right? And you have certain transactions, they look and rate movies, and then you want to basically recommend to, you know, people that maybe have a similar personality looked or rated, let's say, some movies the same way. So those that they didn't look at, you maybe want to do a good recommendation. But this is something what we will do much later in the course, after going also to after deep learning, but it's still something what is used daily in cloud computing and also daily with big data. You can imagine the data that Netflix now has to analyze its users is quite substantial. But I stop here now for the second part and see you soon in the third course hours.